Where are we? We had a 1 week pause and we arrived at discussing Fourier transforms. Why Fourier transforms? Because we were discussing Laplace transforms. And why Laplace transforms? Because we saw that the integral, that is the convolution in time, in a certain sense, it's an operation that from an embedded system perspective is computationally hard. And we got a glimpse that by moving time into frequency, convolution, that is an integral in time, becomes a product in frequency, and we kind of have the possibility of using some lookup tables to do computations very fast. How much are we together on this concept here? Very much together, not at all, kind of. We have to be there. Laplace is a tool for us. And what is Laplace? Laplace is an extension of Fourier. And what is Fourier? Fourier, now we go through, is eventually kind of a pattern matching algorithm. Definition is essentially the same definition that we have whenever we have Fourier, Laplace, only that with Laplace we've got, instead of j omega, we have s. This one is real, this one is purely imaginary, this one is complex. In a certain sense, Fourier is one-dimensional, Laplace is going to be two-dimensional, and we will see very soon why this. Okay. If I remember correctly, we were kind of here where we were doing the concept of Fourier in a very informal way. I was also suggesting you to watch the videos. Did you watch the videos? I hope so. If you watch the videos, this is going to be very easy and a repetition. What is the stuff here? This is a complex signal. How is a complex signal? It's in time. This is a rotation. Okay? And then what is this stuff here? This stuff here is actually the signal that I have whenever I consider only the real part of that rotation. And this one, what is this one? It's basically what I get here. It's actually a sign. And there's a j, so eventually you see it's this one is a rotation. This one is this part here on the imaginary plane. Are you following me, the drawing? Perfect. This other part instead is what? It's essentially this projection here of the complex signal. And whenever we are looking at those two, this and this, they are virtually the same object, because a cosine and a sine is the same object, just shifted. True? And it's essentially a matching operation, in the sense that ignore this part here for now. R2, x1, x2. This vector here and this vector here. What does it mean to do inner product of those two vectors from a geometrical perspective? How many of you know about inner product? I am an inner product. What is this? Is it something to eat? I have heard about it, but I do not know what it is. I would like everybody to say. Okay, perfect. At least the vast majority heard about it. How similar are those two things? Imagine a similarity measure that is eventually kind of proportional to the angle. So that if those two vectors that we want to see if they are similar, if they are aligned, then this similarity measure is going to be the length of vector 1 times the length of vector 2. This is kind of a similarity measure. True? If they are aligned, I multiply their length. If they are orthogonal, the similarity is 0. And if they are not orthogonal, what do? I do similarity measure equals length 1 times length 2 times cosine. Sine or cosine? Cosine. Cosine of the angle. You see that in a certain sense, the length of the cosine, the length of the vectors matters, but also the angle among the vectors matter. True? This is, let's call it A1, A2, and this B1, B2. You saw an operation that is this kind of similarity measure equals A1, B1 plus A2, B2. This operation, you saw it, true? This operation, you already saw it, true? How many of you saw this formula before? Plus 1 plus 1 minus 1 plus 1. Let's take those two vectors. If I do this operation, what do I get? 0. Why? Because whenever I do the inner product, that is eventually this object here, the inner product is that object there, true? You can normalize by the length, but let's ignore the normalization. The angle matters in the sense that whenever we've got orthogonality in R2, and we do this product here is going to be 0. True? And if I do this one and make it longer, and I do plus 3 minus 3, this product is still 0. Are you together with me or not? 1, 2, 3. Perfect. R3. Oops, let's make it in this way. We have vector 1, V1, and vector 2, V2. How do I define in a three-dimensional space the inner product between those two things? Will be A1, B1 plus A2, B2 plus A3, B3. Are we together? Yes. And guess what happens whenever they are orthogonal in the geometrical sense that you have in your mind? This one is going to be equal to 0. True? And if instead they are not orthogonal, that number is not going to be 0. It's going to be something that is somehow the angle between the two. You are following me, true? Perfect. And if I've got something that is 7-dimensional, 8-dimensional, this one is going to be plus A4, B4, plus A5, B5, plus A6, B6, true? And that whenever they are orthogonal in the geometrical point of view, that inner product is going to be 0. If they are not orthogonal, it means that somehow we've got an angle that is different from 0. Sorry, from 90 degrees. I do not know if I said it right, but you got the point. We are together. Perfect. Now, let's assume that V1 is 100-dimensional and V2 is 100-dimensional. Okay? How can we represent V1? If it is 100-dimensional, I might also do like this. K, 1, 2, 3, blah, 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 100. And then I've got something that I should do with points. It should be something like this. True? But I can also visualize it just because I'm a little bit lazy. Something like this. You got the point? This is V1. True? And let's say that this is V2. What does it mean to do the inner product? It means to take A1 times B1 plus A2 times B2 plus, you got the point, I'm not here, it's here, plus A3 times B3. True? And those are actually vectors in 100-dimensional spaces for which if the inner product that is, what's out? What am I doing? It's point-wise multiplication of the two, true? And then I'm summing up. True? I am summing up in I, AI, BI. Let's write those two signals as time signals. It's going to be signal 1 of K, signal 2 of K, true? And in I. Together? Are we together on this? Let's make a different name. Instead of signal 1, let's call it F of K, H of K. True? And now let's do that. Instead of having 100 samples, we have what? 1 million samples, 1 billion samples. Let's make them become continuous signals. What is it going to be? So, in decades. Are we together? Are we together that that integral that we see here? What is it? What is this integral here? It's an opportune infinite dimensional extension of an inner product that is looking at that angle that is a similarity pattern between the cosine and f. How much are we together? 1, 2, 3. So if we have this vector and this vector that are going from t minus to infinity and t plus infinity, and they match, and we do the integral everywhere, this stuff here might go to what? To plus infinity. Or minus infinity if one is the opposite of the other one. So if I've got those two vectors here, and we try to do the inner product, we get minus product of the two lengths. True? We are together on this, people? If this one is a cosine, and this is a cosine, cosine omega t, cosine squared, integral of a cosine squared, what is it going to be? Integral of cosine squared. Cosine squared will look like what? Sorry. True? This is t, this is cosine squared. If I take the integral of this stuff here, it's going to be plus infinity. We see. So, if this is equal to omega, this stuff is always positive, this stuff goes to plus infinity. True? But if this one is slightly different from this one, this integral goes to, try to think about it. Think about it, discuss about it. Let's see if your intuition goes. In the while, I put a plot, and then with the plot, you're going to get it, I'm pretty sure, pretty right. But in the while, think about it. Is the question clear? I've got this cosine, that is this one, and this cosine, true, that is this one. They have frequencies that are slightly different. True. We do the multiplication time point to point. You see, it's point to point multiplication. We get another signal, and then we integrate. What do we get? Discuss. The way I take the plot. So people, I let you discuss. Go. Where are we? Does anybody want to say? Does anybody want to say? What should we get as an integral? So here in this zone, we see the product of the two multiplications, of the two cosines, true? This is the convolution operator, so in a certain sense, it's not exactly what we were drawing there. But think about extending the blue infinity here, extending the green infinity there. We would get this pattern repeated, true? If we do the integral of that repeating pattern, the area that we get is going to be the limit. I assure it's going to be 0. Because so much positive stuff, so much negative stuff. Okay? And eventually you balance out and it's 0. If you take it as an opportune limit, but we are doing intuitions up to now. What do we have? Let's make a plot. Let's call it frequency. And then we have this omega and this alpha here. Whenever the two match, this one goes to infinity. True? Whenever the two are different, this one goes to 0. True? Perfect. Now, let's take a plot that is slightly different, that is though the same. This one is something given. Let's assume that we have a spring mass system without friction. True? It means that we have a certain mass, we have a certain elastic constant. It will oscillate with a certain given frequency that is proper of the physical system that we have. True? So let's pretend that this one is my impulse response. I hammer the spring mass and it starts oscillating. True? My h of t for this physical system is going to be a certain sinusoid, certain cosine. Okay? Means that this one is fixed. Let's put it 10t. Okay? Okay, that is fixed. At this point, what do we have? Omega. Let's call it star of omega. That is this index here. This is 10. How will it look like? 0 plus infinity, 0. True? Together? Do we see it? Of course, whenever we have omega that is 9.9999, we are going to have two sinusoids that are very close. Let me do another one that is... this is the situation. The closer the sinusoids are, the closer the sinusoids are in terms of frequency, the longer it will take for this product to kind of do this behavior. True? We see it? But it's still averaging to 0 whenever I do the integral, minus infinity plus infinity. So we have a behavior that is like this one. And for negative frequencies, if I take negative omegas, what do we get? Cosine of omega t and cosine of minus omega t, how do they behave? The same. True? Because cosine is symmetric. How much are we together, people? Very much? Not at all? Kind of. Because I do not know how fast to go. Perfect. We are going to have something that is like looking the same. It's 10. Okay, you got the point. It's drawn in a bad way, but you got the point. Okay? And this is a plus infinity 1. If I was having 3 cosine, this would be a plus infinity, but I might do something that is 3 long. So to indicate kind of I've got 3 cosine. So it's an informal way of seeing things, but this is instrumental for this exercise here. I do this sweeping thingy. This is omega, and I see something looking like this. This is 1, and this is 2.5, and I got that kind of a similar thingy. And this is 3, and this is 14. F of t equals, you tell me. Go, discuss. The integral of a sum is the sum of the integrals. True? The integral of a sum is the sum of the integrals. Here I see 2 spectral lines. Those are the spectral lines. True? Two 2.5. I got it. I would have gotten it in 2 minutes more. I'm lost. Be honest. It's for me. So, people, integral of star plus square times triangle is going to be integral of star times triangle plus integral of square plus times triangle. Are we together on this? We are together on the distributivity of integrals with respect to the sum. Perfect. In a certain sense, if this signal here is a cosine of something plus a cosine of something else, it's kind of having 2 spectral lines. True? Are we together on this? And then that visualization, I was having kind of a 3 here, just to, or 2.5, just to highlight that one cosine was a little bit better, bigger in a certain sense. Okay? Are we together? Another question. Let's assume that I've got integral of this f times cosine omega t, and I've got omega here, and I have something that looks like this. What does it mean? What does it physically mean? This is omega, and this is my star of omega. In a certain sense, this is finite. True? And whenever I take this specific omega, it means that this one is a specific oscillation from minus infinity to plus infinity. True? But I've got a finite matching. It's a finite matching now. True? If I look at that specific omega, star of omega is 10. What does it mean? It means that very likely f looks something like, now it's made in a bad way, but imagine an f that looks like this one. True? F goes to 0. True? But I've got that f multiplied times that cosine with that specific frequency, they kind of match. True? So I kind of see that they are matching, but it's not a infinitely equal thingy. And then, of course, if I take a slightly different omega and I take this omega here, it means taking something that is slightly different, but maybe still I've got some resemblance. Okay, whenever the f is not something that has got infinite support, but has got a finite support, we kind of go down from infinity matching to a finite matching. True? The same stuff. Okay, this one is the stuff that I wanted to say. Blah, 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 blah. And this stuff here is similar, only that we are kind of doing a matching with another signal. So it is a sign. What's out now? If I have f equals to sine of 10t, whenever I take omega equals to 10, I've got sine squared, and my matching is going to be to plus infinity. True? Together? But whenever I take minus omega, minus 10, sine of minus 10t is minus sine of 10t. True? We get minus infinity. Do you see it? The parity and disparity of sines and cosines. See that we get minus integral of sine square. I see it. I don't see it at all. Kind of see it. Perfect. So in a certain sense, whenever I do the matching with the signs, we have this kind of disparity thingy, but somehow we are doing it. And now something very interesting. Matching with a cosine, matching with a sine. And then the J component. Maybe it's better if I do it here because I think that I do it better here with what I saw up to now. Omega, real part, imaginary part. This one is what? It's my integral f cosine in the t. And this is J integral f sine. Okay? If f is a cosine, I'm going to have what? If f is cosine of 10t, I'm going to have something that is like this. True? If f is sine of 10t, I'm going to get something that is like this. Yes, because it's aligned with the imaginary axis. True? Do we see it? And if I get something that is slightly off, what does it mean? It means that this one is what? Plus some phase. Let me show you what I mean. Are we together that this one is not aligned this way, it's not aligned this way, it has an angle, and it's not aligned this way, okay? Are we together that those two infinities, I'm putting them at an angle? Are we together that cosine and sine are the same thing, only shifted 90 degrees? Are we together on this? Perfect. So, if this is my cosine and this is my f, whenever I multiply the two of them, I get cosine squared. True? If my f is not anymore cosine, but is cosine plus a shift, it's going to be something that looks like this one. True? Are we together? If the shift is not 90 degrees, if I do the product of those two, what do I get? I get something that looks like this one. Let me show you. this one. You see, here there's a shift. This is the product of the two cosines that are the same, just slightly shifted by the offset. True? The area that we get, this one repeats from minus infinity to plus infinity. True? Do you see it? The area that we get is going to be plus infinity still. True? But not 1 plus infinity, 0.7 plus infinity. Do you see it, people? 1, 2, 3. And of course, this is blue is my sine of omega t plus 10 degrees. And I will try to match it with sine of omega t and cosine of omega t. And if I take cosine of omega t, this matching still will go to infinity with a certain number. True? Do you see it? Do you see it? Do you see it? I have an f that is a slightly translated version of a sine. So it doesn't start in 0. It doesn't start in 1. True? So it's slightly off. True? It's this blue line here that is slightly off. It will match plus infinity with a cosine, and it will match plus infinity with a sine. True? Not 1 plus infinity, 0.7 and minus 0.2, for example. True? We might also have a negative number. True? Let me do it. True? This shifting is a minus 0.9 plus infinity. I see puzzle faces. Do you see what I mean? This area here, this area, if I take this one and repeat it everywhere, and I take the integral from minus infinity to plus infinity, what do I get? Minus infinity. True? Also, this one is minus infinity. Bigger minus infinity. Do you see it? It's wrong. I'm saying something that from a mathematical perspective is wrong, but I want to give you the intuitions. The intuition is this one. We have, whenever we do the matching, it will go to plus infinity, it will go to plus infinity or minus infinity, but one will go to plus infinity a little bit faster than the other plus infinity. That means that we have an angle in a certain sense. What is this angle? This angle is this. Very much together, not at all, kind of. That it means, I see several tools, it means that there must be some question. I redo it. I redo it, and then let's try to see. I have omega laying down here. Real part, with this real part, I mean trying to match with cosine omega t. And then with this one that is vertical, this one, imaginary part, it's trying to match with sine omega t. How much are we together up to now, people? 1, 2, 3. If I draw something like this, it means that in a certain sense it's laying down on the real omega plane, okay? This would indicate what? Would indicate that my f is a cosine of omega bar t. True? How much are we together on this up to now? 1, 2, 3. I'm drawing the angles in that kind of wrong way because this angle and this angle, you got it's in that plane. Okay. If instead I was having something that was looking like this, up, down, this would be plus 90 degrees. True? True? Now we have this situation, and that situation. If I measure something that is in between, what does it mean? This one is not anymore 90%, 90 degrees, might be, I don't know, 73 degrees. You get the point? Because those two areas kind of have a relative size. Together, not at all, kind of. Just for me to see. And don't worry, people, this part here is very important, and we kind of go. Are there other questions? Is it clear, this? So it still goes to plus infinity, okay? But in a certain sense with a certain angle, because there's a shift. Because we have a situation that is kind of this one. This is blue, that is matching with a cosine, and this will be the minus infinity. It will be actually in this direction at this point. It should be kind of like this, probably. But you get the point. And we assign another value. Question.
So in the case where we have a phi, we have both an imaginary and a real part. Whether in the two limit cases we have just imaginary and just.
Indeed. Okay. Indeed.
And also, I'm not sure about what you said about, for example, the continuous function, the one that you represented before.
Indeed. Now we go to that case there. Are we together with the spectral lines? That means that we have something that goes to infinity. We got the point. If we have something that looks like this one, what does it mean? I've got a certain cosine with a certain frequency, another cosine with another frequency, a certain offset, shift, phase shift, and another phase shift. Together, was it a question, or did you want to say that it was clear? Okay. Perfect. Now, if we take f that is something that is somehow a function with finite support. Before we were saying that if we look at only looking with cosines, we might get something that looks like this. True? Those two curves are in the real plane. Are we together? If we think at them matching with sines, we might have something that is like now I've got to be careful with the I say like this. I'm bad in drawing. I should kind of get something. This blue stuff is in the imaginary plane, true? In the vertical plane. Are we together on this? Are we together? Then, if we think at omega, we are going to get what? Something that is a combination of the 2 points. For every omega, I will have a real part and an imaginary part. True? Do we see it? It means that actually those two curves that are single dimensional, they follow from something that is in 3D, in the sense that this one is the actual pattern that I get. For every omega, we'll have a real part and imaginary part. That is a matching with a cosine and a sine of a function that has got this limited support. Okay? So that basically by projecting, by looking just at the real part or looking just at the imaginary part, these stuff, that is a line, it's like a thread. True? Do you see it as a thread? It becomes either the gray one, that means how similar to a cosine is, or the blue part that is how similar to a sine part is. Together? So, let's redo it. Whenever we do Fourier transforms are basically taking f, transforming it into this way. You typically see not this plot here, but you see the plot for which you look at magnitude of f. True? That is essentially taking this thread as a complex number and thinking at, for each omega, the modulus of this number, and you get this object here. So, are you together? Because you don't care about the phase. Because whenever you take the modulus, it's kind of ignoring this part here. You see? How much are we together, people? 1, 2, 3. Other questions? Then let's stop here.